Dear students, today we are going to talk about the expression for refraction at any spherical surface. But before we really talk about it, I would like to revise the meaning of image and types of image. You see, if any object is placed in front of, say, a lens or a mirror or any spherical surface, then its image is formed somewhere. That point is the point where the rays emerging from the object after reflection or refraction meets really or appears to meet. That point where these two rays intersect, not only two, all the rays emerging from the object essentially meets or appears to meet at some point after reflection or refraction. That point is known as the image of corresponding point of the object from where the light has been drawn. Means the light emerged from which origin, it is the image of that origin. So we have two type of image, one real image, another is virtual image. Real image are those points where the rays after reflection or refraction really meet, and virtual images are those which are those points where the reflected ray or refracted ray, those ray coming from the object after reflection or refraction, do not actually meet there, but they appear to meet there. So this is the basic definition of image. Now we talk about the refraction formula for any spherical surface. We have assumed that the object lies on a rarer medium in front of a convex spherical surface which separates the two medium, rarer medium and denser medium. Mu1 is taken as the absolute refractive index of the rarer medium, and mu2 is taken as the absolute refractive index of the denser medium. Now we have assumed an object to lie at some point O on the principal axis, and we are selecting two rays emerging from this point object O. One is moving along ON and another is moving along OP, and after refraction they meet at some point I1, which will be the corresponding image of this object O. And you can very well understand that angle of incidence is the angle made by incident ray with the normal. And so here we have a normal. What is normal? A line passing through the center of curvature, that is the radius is always perpendicular to the tangent at the point, so on the spherical surface, and so line joining NC will be nothing but normal at point N, and the angle between the incident ray ON and this line will be angle of incidence I, and angle between the refracted ray and the normal at the point of incidence will be angle of refraction, which is represented by a small r. Now if you look at this triangle NCI, you see that the exterior angle gamma must be equal to the sum of interior angles r plus beta, and therefore we have from triangle NOC, in the same manner we have alpha plus gamma is equal to I. Alpha plus gamma is equal to I, because exterior angle I is equal to the sum of interior angles. And again, in the same fashion, from triangle NIC, NI1C, we have just talked that gamma exterior angle will be the sum of interior angle R and beta. So gamma equal to R plus beta. Gamma is equal to R plus beta. Now here we do some minor manipulations for our comfort. What we take is, we take that these angles I and R corresponding, all the angles will be certainly, if one of it is small, others all will remain small. So we are taking small angles, and for small angles we can approximate sin I is nearly equal to sin I, and therefore we have written I is nearly equal to sin I, and I is equal to alpha plus gamma. So we can write for small angles alpha is nearly equal to tan alpha and gamma is nearly equal to tan beta, and so we have written sin I is nearly equal to tan alpha plus tan gamma, and we put the value of tan alpha and tan gamma from the figure. Here you see alpha is, this is alpha angle, so tan alpha will be perpendicular, that is Nm divided by Om. So Nm divided by Om is tan alpha, and for tan gamma we have tan gamma, for gamma is, this is gamma, so we, for tan gamma we have Nm divided by Cm. Nm divided by Cm, and therefore MC, and therefore we make, now further we make some approximation that as this point M is very close to point P, P is the pole of the spherical surface, we can write OM, for OM we can write OP. OM is the, of this much value, it can be approximated to be equal to OP. Why we are doing this? Because we want to write the certain terms in standard terms format. What is the standard format? Object distance. Object distance is OP. So instead of OM, we prefer to express it in terms of OP. Similarly, we replace CM value, MC value in terms of PC. For PC is what? What is PC? PC is equal to the radius of curvature of the spherical surface. And therefore, we got it in standard format. For PC we can write R1, and for OP we can write minus U using the sign convention. So we got this expression for sin I, we got the value of sin I, and similarly here we have R equal to gamma minus beta, and for small angles we write R nearly equal to sin R, and for small angles we write gamma is nearly equal to tan gamma and beta is nearly equal to tan beta. Now again we put the value of tan gamma from using this relation. You see gamma will be equal to Nm by Cm. Nm by Cm minus tan beta, where you see tan beta, this is angle beta, so tan beta will be Nm upon Mi1, and therefore since M is lying very close to P, therefore we can replace Cm by Pc and Mi1 by Pi1. Again we want to convert it in some standard format, because PC is equal to the radius of curvature and Pi1 is equal to the image distance. Now we use the Snell's law. From Snell's law we have sin I by sin R is equal to absolute refractive index of second medium divided by absolute refractive index of first medium, and so on cross multiplying we get mu1 sin I equal to mu2 sin R. Now for sin I we have found the value of sin I. Here it is Nm by OP plus Nm by Pc. So we write mu into Nm by OP plus Nm by Pc, and for sin R we have found its value, Sin r is nothing but equal to Nm by Pc. So Nm by Pc minus Nm by Pi1. Now in this expression, what you see, Nm is common in both, on both sides, so they get cancelled. So and then taking mu1 inside the bracket, mu2 inside the bracket, what we get is mu1 by minus u1 minus u, mu1 by OP. And what is OP? OP is object distance. And why we are writing minus sign? We are applying the sign convention. And when you put the value of PC, you get mu1 by PC. For PC you have plus R1, because we are measuring this distance along the incident ray, and so we get mu1 divided by minus u plus mu1 divided by plus R1 equal to mu2 divided by R1 minus mu2 divided by V, because V is image distance, and since this distance is measured along the incident ray, therefore it is taken as positive according to the sign convention. Now if you place the term carrying R1 together, what you see, mu2 by R1 is there, and when you carry this mu1 by R1 on the right hand side, you get mu2 minus mu1 divided by R1. And if you carry this term mu2 by V on left hand side, what you get is mu2 divided by V minus mu1 divided by U. mu2 divided by V minus mu1 divided by U. So this is the expression for refraction at a spherical surface when object lies in a rarer medium in front of a spherical surface, dividing it from the denser medium. Now it is, you can find by drawing the figures having a spherical surface concave on the object side, and object is kept inside in a rarer medium, still you will see that this same expression will be derived. Means it is not going to affect this expression for refraction at a spherical surface if the body lies in the rarer medium, and whether the surface is convex on the object side or it is concave on the object side. Means if it is curved in this way, convex on the object side, we got this expression. Now even if the surface is not convex on the object side, it is concave on the object side, still provided the body remains in the rarer medium, still you will get the same expression. You try this, take it as a homework and verify the statement which I have just stated. Apart from this, whether the image formed is real and whether the image formed is virtual, again you will get the same result provided object lies in the rarer medium. So that means we conclude that, you verify it, we conclude that whenever body lies in a rarer medium, the refraction formula will remain same as equation 1a. Now we take a different case, case 2, when object lies in a denser medium and it lies in front of a spherical surface which is concave on the side of object. You will have this type of diagram. Object is over here and we take two rays. This is center of curvature, and then object one ray is incident at point N on the spherical surface. Due to refraction, it will move away from the normal, and say the image is formed at some point I2 which is real, and then from this diagram what you can again write is the exterior angle gamma, the exterior angle you see here the exterior from triangle NOC, from triangle NOC you have, from triangle NOC, gamma is equal to I plus, gamma is equal to I plus alpha. Exterior angle is the sum of interior angle. So gamma is equal to I plus alpha, and so we get again the expression for angle of incidence I. We will deal with this expression in the same fashion as we have dealt above here, and also using another relation from triangle NI2C, NI2C. Here you see that well gamma plus beta equal to R. What is R? Let us see that this is angle R. Well, you see this dotted line is showing the normal at this point, and the angle made by refracted ray with the normal is angle of refraction. So we can write exterior angle R is equal to gamma plus beta. Exterior angle R is equal to gamma plus beta. So again we got the expression for angle of refraction, and then we will deal with the expression for angle of incidence and angle of refraction in the same fashion as we have dealt above here, and then applying the sign convention, applying the Snell's law, doing the same thing, everything, except the difference will be that here we have to apply sign convention, which will give different sign to different standards measurements. Say for example, here in this case u will be negative and radius of curvature will be also negative. So we have named it as R2. This distance we have named it as R2, that this distance will be negative, while in the previous case this radius of curvature was positive, and of course object distance is always negative usually. So this u is a negative, it is negative, and object image distance is again positive as we have we got in the first case. So we have to simply apply the sign convention, apply the Snell's law, and then put the value of tan gamma, tan alpha, tan gamma and tan beta, and then solve it. We get this expression, we call it 1b. Well, again what you will find is, you can check it yourself whether the object is placed on the concave face of the spherical surface or on the convex face of the spherical surface dividing the two medium, whether the image formed is real or image formed is virtual. In all case, invariably, if the object lies on the denser medium, the formula will remain same. So now we can conclude altogether that while the object lies in the rarer medium, the formula remains always given by 1a, and while the object lies in the denser medium, the formula always is given by equation 1b. Irrespective of the fact that whether the spherical surface is convex on the body side, object side, or concave on the object side, or the image is real or the image is virtual. One thing what we can also practice to keep these expressions in our memory is that to obtain equation 1b, we we simply exchange mu1 with mu2. You see here mu2 minus mu1 by r. So here you get what you see is if you write it in that form, then let us work it out over here. If you exchange mu1 and mu2, what you get is mu1 minus mu2 divided by r equal to mu1 by v minus mu2 by u. Now if you arrange this in the form of mu2 minus mu1, so what you get is mu2 minus mu1 divided by r, of course minus sign, we can take it like this, and okay, you change it side, and then equal to mu2 by u minus mu1 by v. So you got the same thing, mu2 minus mu1 by r, mu2 minus mu1 by r equal to mu2 by u minus mu1 by v. So we are getting the same result, only we need to exchange mu1 by mu2, and we ignore this suffix r1 and r2. This is how we can get this expression without really deriving it whenever it is required. Now also to memorize the equation 1a, what we can do is always remember final minus initial. So what is final? Second medium is the final medium, denser medium. So final mu2 minus mu1. Final minus initial divided by r, we take it as a dummy or constant. Now here you see on the right hand side, final mu2 is final, and object or image distance, this v is final, that is image distance, minus initial, that is mu1, divided by u, that is the initial object distance. So you got some clue how to keep it in your memory, the expression, the refraction formula for spherical surfaces. We can have some comfort if you have these things in your mind. Now, so we have reduced the various cases of having real image, cases having virtual image, cases having body placed in front of convex side of the spherical surface, or placed in front of concave side of the spherical surface. So 4 into 4, there could be 8 cases, and this we have reduced in terms of 2 cases, and that further reduced by in terms of our memorizing techniques into 1 case. So this is all about the refraction formula at a spherical surface. That's all for today. Thank you and have a nice day.